In this class, we'll continue our discussion of the use of t-tests to test hypotheses of differences between groups or differences in group means. In the last class, we looked at a relatively uncommon situation, the one in which we are testing a single group against a population mean when we don't know the population variance. The much more common experimental situation is one in which we don't know either the mean or variance of the population. When that is the case, we'll compare an experimental group against a control or comparison group in order to test our hypotheses. So let's discuss the most important use of the t-test by creating a slightly different research design. In an earlier class, we imagined a clinical study of a sample of depressed adults in which we randomly assigned some participants to either an experimental therapy for their condition or to a no treatment control group. We would hypothesize that the group receiving experimental treatment will be less depressed at the end of the treatment than the no treatment control group. And if we continue to measure the construct depression using the operational definition of scores on the Beck Depression Inventory, then we would expect the treated group to have a lower mean score than the control group. This is our research hypothesis. Our null hypothesis would be that there is no difference between mean scores of the two groups in the population. We would call this a test involving two independent samples, because the response of the participants in one group on the Beck Depression Inventory will be independent of the response of participants of the other group. In fact, we are hoping the only reason they would fill out the BDI differently, the two groups would fill out the BDI differently at the end of the treatment, is that they had different experimental experiences. Namely, one group experienced a treatment and one group did not. In this type of situation, we will need to rely entirely on sample statistics to estimate what is going on in the population, and really this is what is happening in most experimental situations. We will use the means from each group to estimate the mean in the population, and we'll use the variance of each group to estimate the variance in the population. As a result, our formula for computing the t-statistic will change slightly. In the numerator, we will subtract the sample means from each other rather than from a population mean, which is currently unknown. And in the denominator, we have the standard error, but we call this statistic the standard error of mean differences. So this standard error is different from the standard error of the mean. To see how we get the standard error of mean differences, let's go back to the situation in which we take repeated or infinite samples of, say, size 30, but this time, in each experiment or sample, we assign participants to two different groups, and in each sample, we compute the means for both groups, just like before. But in this situation, we then subtract one mean from another, obtaining what I call the mean difference score. So after an infinite samplings, we would have a distribution of mean difference scores. The standard deviation of this distribution is called the standard error of mean differences, which is the average distance. The difference between sample means can vary from the population mean difference score. Before going to the next slide, see if you can answer this question. If the null hypothesis is true, what will be the mean of the sampling distribution of mean difference scores? The answer is 0. If the null is true, over repeated samplings, the means of the two groups will not differ from each other, and the average difference score will be 0. This is why another important way to express the null hypothesis for the independent samples is to use the expression mu1 minus mu2 equals 0. We will revisit this concept later in our discussion of the confidence interval in a later class. Now, let's return to our example. Let's imagine we have 30 participants, and because we are computing two means to obtain our t-statistic, our degrees of freedom are n-2 for a t-test of independent samples. Further, let's say we obtain a mean of 12 for the experimental group and a mean equal to 20 for the no treatment control group. Now, let's imagine that the standard error of mean differences we found to be 2.50. Essentially, the standard error of mean differences is the average of the standard error for the two groups. However, the computation of this statistic is less important for our purposes than your understanding of what it is. I'll refer you to look at the book for a further discussion of the computation of the standard error of mean differences. Before going to the next slide, please compute the t-statistic based upon this data. If n is equal to 30, what is the critical value, and would we accept or reject the null hypothesis? Based on these data, the mean difference score is 8, which we'll regard as the treatment effect, or the effect of the treatment on the participants. This is then divided by 2.5, which is our estimate of the sampling error, or the luck of the draw. So when we divide the treatment effect by our estimate of sampling error, we find t equal to 3.20. By consulting the t-table, we learned that the critical value is equal to plus or minus 2.048 when degrees of freedom equal 28 and alpha is equal to 0.05, and we use a two-tailed test. Because the obtained test statistic, 3.20, exceeds the critical value of 2.048, we'll reject the null hypothesis. We'll then conclude that the means in the population for the two groups are not equal, and that the treatment group has a lower mean score on the Beck depression inventory than the control group. At a construct level, we may conclude that adults treated for depression have lower levels of depression than those who are not treated. We might also approach the interpretation by saying that the two groups do not come from the same population. The experimental group comes from a population we might call depressed adults who have received treatment, with a mean for that group estimated to be equal to 12. And the control group comes from the population of depressed adults who do not seek treatment, with an estimated mean in that population of equal to 20. In all the examples used so far in this class, I've asked you to use a two-tailed test, which is the most common type of test. In a two-tailed test, we are essentially testing that the mean could not only indicate that treated individuals have less depression, but that the study could also find that the group receiving treatment actually got worse, and a significant finding in the opposite direction would essentially demonstrate that fact. When researchers feel that such an outcome is not critical to their area study, they may wish to study a directional hypothesis, namely that the mean Beck depression inventory of the treated group will be lower than the mean of the control group. When testing a directional hypothesis, researchers will conduct a one-tailed test and find the critical value that cuts off the upper and lower end of the t, that cuts off only the upper or the lower end of the t-distribution. Before going to the next slide, find the critical value for the example we just worked through if we had decided to conduct a one-tailed test. The critical value using a one-tailed test is 1.701, which is much smaller than the critical value for the two-tailed test of 2.048. Thus, if the actual finding of a study is in the intended direction, a one-tailed test is more powerful than a two-tailed test.